Okay, good afternoon. Let's continue with our discussion of op amps. Ideal op amp there. Okay. So we had, let's see, we stopped right here where we had the virtual ground, virtual short concept. And so far our discussion has been about op amps in open loop, meaning the output has no connected pathway to the input, right? No pathway to the input. So instead of open loop, now let's say we close the loop between output and input. So we take the output and we connect it back to the input. Depending on where we connect it, if we connect the output to the negative terminal or the inverting terminal, we say it's negative feedback. If we take the output and connect it back into the positive terminal or the non-inverting terminal, we say it's positive feedback. There are advantages to both approaches. There's upside and downsides to both. If you have negative feedback, meaning the output, a portion of the output is fed back to the input, meaning it's out of phase, we can inhibit the input signal. Okay, we can inhibit the input signal, meaning the input signal is now being reduced. So you have an amplified output, but you feed it back into the inverting terminal, input is again decreased. So there are advantages, namely increased signal to noise ratio, SNR is increased, and increased bandwidth. Okay, the response is also quite linear. Positive feedback increases the gain response, it's adding on. However, it narrows the bandwidth and it encourages oscillation. Okay, bandwidth is basically the frequency range between which it can operate. Positive feedback is more commonly used for oscillations or oscillators, which are used for signal generation. Negative feedback is very useful for amplifiers. As amplifiers. Inverting configurations are also used for a real life example. They're used in noise cancellation. If you have a signal and you invert it by 180 degrees, the resulting output would be 0. So if you have an inverting amplifier, you can use it to invert your input signal. Any noise signals that are captured can be inverted 180 degrees, added on to the same noise signal, your resulting output would be 0. That's noise cancellation. Okay, so let's look at negative feedback first. What happens when you take an op amp, no other external circuitry, but you take the op amp and simply connect it to the inverting terminal. Well, what happens then is that the output is exactly the same as the input. And I'll explain why. Let's say Vin increases. Okay, as Vin increases, Vout would also increase. Now Vout is of course a function of the gain A, right? So let's say Vout increases, well, but that is fed back into the negative terminal. Now, the properties of the negative feedback is that it would reduce the Vin going into the op amp. And because Vn is now being inhibited, as soon as Vout increases, this cumulative effect will be that Vin decreases. It's trying to force Vin to go to 0. And Vin, in this case, the difference that is going into the op amp. And because that is forced to go down to 0, Vout goes back to 0. It's a loop, and that loop happens at a very fast rate. I wouldn't say instantaneously because nothing takes place instantaneously, but it happens at a very quick pass phase. You connect your circuit, apply the input signal, flip the switch on. Before we can blink, output is equal to V in. So the overall effect, overall result is that V out is equal to V in. V out is equal to V in. So the question to ask is, if V out is equal to V in, what is the purpose of this circuit, right? Well, one of the names of this circuit is that it is a voltage follower. VO follows V in. Again, V in is applied, V out increases by negative feedback. So again, forces V in towards to go to zero. And when it goes to zero, again, V out and again in loop. So the circuit is known as a voltage follower. You apply a sine wave signal to it, you get the exact replica at the output. It is used to isolate two different circuits. So it is used as a isolation amplifier or a buffer circuit to provide a buffer between two circuits. Okay, and I can will show with an example. Let's say you have a laptop adapter or laptop charger. Most laptop adapters or chargers are around 18 or 19 volts, or even 20 volts. Your laptop adapter has only one output, but your laptop system requires multiple voltages. There's a CPU voltage, GPU voltage. There are other parts of the circuit, display voltages. So all of those require different voltages. Your USB port requires a certain voltage. So what is the output of your USB port? It's standard spec. What is the output of a USB port? 5 volts. And that's why we can plug in our mobile devices into any USB port. The voltage remains constant at 5 volts. Whether it's your desktop computer, your laptop, mobile phone chargers, any USB port anywhere is rated for 5 volts. So if your laptop adapter is 20 volts and your USB port is 5 volts, the circuit that can provide this, and let's just create a simple voltage divider network. You apply plus 20 volts. Let's say this is a resistor for 3K, and this is 1K. Okay. V out here, let's not confuse it. Let's call it Vx plus minus would be 5 volts. Right, 5 volts. So this circuit, this voltage divider circuit is supposed to supply 5 volts to the output. Okay, 5 volts to the output. But now let's say you connect a load, you plug in something into the USB port, and that load has a value of, let's say, 10 ohms. Okay, 10 ohms. What happens then? From here, let's go here. If you plug in a load of 10 ohms, that effectively reduces the bottom resistor to less than 10. Our EQ of two parallel resistors would always be smaller than the smallest value. So if your load is 10 ohms, that 1 kilo ohm resistor is effectively bypassed. All of the current flows through that 10 ohm resistor. And REQ, 1 kilo ohm in parallel with RL, would be less than 10 ohms. If that is less than 10 ohms, then my voltage divider circuit let's call this 10 ohms, looks like this. And now my output is not 5 volts. It'll be less than 1 volt. Does that make sense? It's a simple voltage divider network. So a straightforward example where you are taking your supply voltage of 20 volts and creating a 5 volt dependent voltage source. That 5 volts is supplied to the USB port. But if you plug in a low resistance, low value of low resistor to that port, now your output has dropped to less than 1 volt. So in cases like these, we insert a isolation amplifier in there or a buffer amplifier in there, where output would be exactly the same as the input. And so we could take our voltage divider circuit, output of this should equal 5 volts, and we'd connect this. Oh, negative feedback like this, and it isolates it from your RL. Now your RL could be any value, but your V out will remain at 5 volts. No matter what your V in is 5 volts. And you can test this out in the lab. How many of you have finished the lab this week, by the way? Okay, several of you. So an isolation amplifier or this kind of voltage follower circuit is used to isolate two different circuits so that the effect of the load does not affect the driving circuit. Hence, it is also known as loading effect or avoiding the loading effect. Okay. All right, so op-amp analysis. Sorry. All right, so op-amp analysis first requires that we verify negative feedback. First, check if the output is fed back into the inverting terminal. Or output connected to the inverting input. Whether the output is connected to the inverting input. And because it is connected to the inverting input, then that forces the input voltage to the op-amp to go towards 0. Okay, so the assumption would be that the input voltage and the input current are both being forced to 0. And then you apply your analysis techniques. KVL, KCL, and Ohm's law. Okay. So most of the amplifier circuits we are going to look at are all inverting configurations. So the first one up is an inverting amplifier configuration. First, let's verify negative feedback. So here's the output, and a portion of the output is connected to the inverting terminal. Hence, negative feedback is present. Negative feedback is present. So inverting configuration, negative feedback present. Let's look at the other terminals. At the inverting terminal, voltage is referred to as V minus. Non-inverting terminal voltage is V plus. Vx is shown as plus and minus, but Vx typically would be V plus minus of V minus. Non-inverting terminal is connected to ground. Therefore, from virtual short concept, V minus is also forced towards ground. II or I minus is the current that's going into the inverting terminal. I1 is the current flowing through R1, and I2 is the current flowing through R2. We are following the passive sign convention. V in minus plus, the current flows from left to right. It is grounded. But also effectively just show that all of this is connected together. Okay, all of them are connected to ground. What is not shown is plus VCC and minus VEE. Those are implied. Okay. So this is an inverting amplifier, right? So the amplifier, the defining quality of an amplifier is that there is a gain equation for the voltage. So we need to find the ratio of V out to V in. Okay, output voltage to V in. So begin by applying KCL at inverting input. At the inverting input. If you apply KCL at the inverting input, we obtain I1 is equal to I minus plus I2. I minus is equal to 0. So I1 is equal to I2. Both currents are the same. Now we can express both currents in terms of the resistor currents or the resistor voltages. And the resistor voltages can be expressed as the difference in the two node voltages at the two terminals of those resistors. So the voltage for R1 is V in. Voltage here would be 0, V minus. So I can write I1 is V in minus V minus. That would be divided by R1. And I2 would be V minus minus VO, the output voltage, divided by R2. If we rearrange the terms, we know V minus is equal to 0. We rearrange the terms, we can obtain V out or V in is minus R2 or R1. And so voltage gain is a ratio of the two resistors minus R2 over R1. We can also analyze and obtain the same expression by applying KVL at the output. Okay, KVL at the output, and you'll obtain the same expression. Yes. So the assumption is that because of negative feedback, V in is being forced towards 0, and so I in is also being forced to 0. The other assumption also is that the op-amp has infinite impedance, so the effective current going into the op-amp is as close to 0 as possible. The assumption is that the input is 0. Okay. In some books, R2 is referred to as the feedback resistor RF, and R1 is referred to as RI or Rin. So again, R1 would be referred to Rin, in for input, and R2 would be referred to RF. RFF would be for feedback. So it would be minus RF over Rin or minus RF over RI. The exact same thing, difference. The minus sign, of course, indicates that it's 180 degrees out of phase, so it's inverted. Okay. This is by far the simplest and most straightforward of the amplifier circuits. But one of the downsides is that if you wish a specific gain, you are limited, right? You're limited by the design of the circuit. The gain is limited to RF or Rin or R2 or Rin. And resistors are only are sold in specific values. Okay, 100 ohms, 220, 330, and so on and so forth. So if you want a very specific gain value, then you have to create a slightly different circuit with more resistors in the feedback path. And I have that problem later on in just a couple of slides. Let's see. The next one up is summing amplifier. Okay, summing amplifier. So in the summing amplifier, as the name suggests, the circuit functions as a adder. It performs the mathematical operation of addition, summing up the inputs, hence a summing amplifier. If you look at the circuit, we again have negative feedback. So we can use the same analysis techniques. Negative feedback is present. Non-inverting terminal is grounded. So V plus is 0. Plus V minus can also be considered to be 0. We can have IA, IB, and we can also state VC. And so it's IC. We can have multiple inputs. Doesn't matter how many, 2, 3, 4, 5, 6, will still work. This is your feedback resistor, IF, so current IF, and II, or I minus, is still equal to 0. We use the same techniques. We apply KCL at the inverting input. So we obtain the sum of all three individual currents is equal to IF. IA plus IB plus IC is IF. IA can be written directly as VA over RA plus VB or RB plus VC over RC. And IF can be written as V minus of VO divided by RF. V minus is at virtual ground, so we can write as 0 volts. Rearrange the terms, and we can obtain V out as minus RF or RA times VA plus RF or RB times VB plus RF over RC times VC. If we choose all resistor values to be the same, not equal to RB is equal to RC is equal to R, then I can write VO is minus RF over R times VA plus VB plus VC. The resulting expression is the sum of all the input voltages, VA plus VB plus VC. Let's take a pause. Let me know if you have any questions. Okay, so again, the name operational amplifier indicates you can use the circuit to perform a variety of mathematical operations. This is one of those operations where you can perform addition or summation. By its very nature and construction is a difference amplifier, differential amplifier, right? So it amplifies the difference. This is an example where you can amplify the sum of input signals. So mathematical operations of subtraction and addition. If you wish to have the same gain for all inputs, then you choose the same resistor values. If you wish to apply different gains for the different inputs, then we choose different values for RA, RB, RC, RD, so on and so forth. No matter what we choose, the output is a sum of all the input signals. We all see, for whoever has done this lab, did you all see that? That's a summation. Okay. So as I was saying, if we wish to have a different gain or wish to have control over our gain, then we build a different kind of circuit in the feedback path, which is right here. We use more resistors. This requires a longer explanation, so I think in the time remaining, we will not be able to cover it. So what I want to do is, what I've done for the previous section is, we'll cover this on Friday, but I'm going to have my annotations written out before class, so students can review prior to coming to class, and then I can go through the steps on how the circuit works. Okay, I think there's a homework problem that is similar to this one. So, once you get started on the homework, you can go through the other problems and the other questions. And of course, you can answer this one also if you want. But I'll have my annotations on here shortly after class ends. Actually, today I have lab from 3 to 6, so I'll get it done sometime later tonight. So my annotations should be on there shortly. Okay, not shortly, sometime today. All right, let's look at non-inverting amplifier. So non-inverting amplifier, input is applied directly to the non-inverting terminal. Negative feedback still exists. You're taking the output and feeding it back into the inverting terminal. So negative feedback still exists. So negative feedback verified. So VI, the difference between the two, can be assumed 0 because we're also connecting the negative terminal to ground, or towards ground, right? II is here. And we can assume that VI and II are forced to go to 0. Okay, forced to go to 0. Again, this is only for the purposes of analysis. Okay, theoretical analysis. So we are saying VI and II, that is the voltage and current going into the op-amp, is being forced to go to 0. Okay, because of negative feedback and the connection. So we can state also because of virtual short, if the voltage at the non-inverting terminal is V in with respect to ground, because we say both terminals are virtually connected together, virtually the same potential, for purposes of analysis, we can state the same voltage appears at the negative terminal because of virtual short. And we can analyze the output loop like this. So if we take the output, we have VO across RL. That means that across R2 and across R1 also we have VO. But the voltage across R1 is V1, and V1 is equal to V in. From circuit analysis of the output loop, I can see it's a voltage divider network. So I can write V in is a fraction of V out, and that fraction is given by R1 over R1 plus R2. If we rearrange the terms, I obtain V out over V in is equal to R1 plus R2 over R1. Therefore, the gain expression AV is 1 plus R2 over R1. 1 plus R2 over R1. Inverting amplifier, it's minus RF or R in, or minus R2 or R1. Here it's plus 1. Okay, 1 plus R2 or R1. Again, inverting amplifiers and non-inverting amplifiers, the input is being applied to two separate terminals. but the feedback in both cases is still going to the negative input or the inverting terminal. So negative feedback still exists. Those are the circuits we are looking at. We are not looking at anything else. These are the only circuits we are looking at. Okay. Again, it's not positive feedback. Circuits are still negative feedback. We're not looking at oscillators. Now, we saw a summing amplifier using inverting configuration. This is an example of a summing amplifier using the non-inverting configuration. Negative feedback still exists. All we have here is multiple inputs going to the same input terminal. Okay. So there's a small derivation for this one. Again, skipped over this one for the previous section, so I'm going to do the same. We'll cover this on Friday. Okay, cover this on Friday. And what we went into was a active low pass filter. Think back, if we think back to 201, how many of you remember filter circuits? What kind of filter is this? Let's analyze quickly. Okay. Capacitor impedance, ZC is 1 over omega C, 1 over 2 pi FC. If F increases, ZC decreases. If F decreases, then ZC increases. High frequencies, capacitor appears as a short circuit. Low frequencies, capacitors appear as an open circuit. Okay. So as F tends towards 0 or at low frequencies, capacitor is open circuit. V out is equal to V in. As F tends towards infinity, capacitor behaves like a short circuit. So V out goes to 0. So is it allowing low frequencies to pass through, or is it allowing high frequencies to pass through? High frequencies are being blocked. When at high frequencies, V out goes to 0. At low frequencies, V out is equal to V in. So it allows low frequencies to pass through. Hence, it is a low pass filter. Low pass filter, LPF. If you switch the output location, if you take the output across the resistor instead of a capacitor, the same circuit functions as a high pass filter. No difference. So if you have a series connection of a resistor and a capacitor, output across the capacitor would be a low pass filter. Output taken in across the resistor is a high pass filter. Anyway, coming back to our circuit. So the filter circuits that you're seeing on the right is a passive configuration. It's only passive components. We are not performing any amplification of the input signal. Hence, it is known as a passive filter. If we take the same filter circuit and we connect it to an op-amp, we can now provide a gain or an amplification to our input signal at our desired frequency. And hence, it is known as an active filter. And this is an active low-pass filter. Okay, this is an active low-pass filter. So if we stick with the same concept and analysis, as F tends towards 0, capacitor is open circuit. Your OpAmp circuit is simply a inverting configuration. Right? V out is equal to the gain times V in. Make sense? Right? Capacitor is in the feedback path. If the capacitor behaves like an open circuit, the resistors R1 and R2 will simply give us a inverting configuration or an inverting amplifier. As F goes high and tends towards infinity, capacitor behaves like a short circuit. And so, do you have? You have a short circuit in the pathway. Because you have a short circuit in the pathway, and the non-inverting terminal is connected to ground, we can say the inverting terminal is also at virtual ground. And because it's at virtual ground, our V out is also 0 volts. V out is forced to go to 0 because V in is forced to go to 0. So the capacitor provides a pathway, a feedback pathway for the output to go towards 0 volts. So in terms of frequency of operation, high frequencies, V out goes towards 0. Low frequencies, V out is an amplified factor of V in. Hence, this works as an active low-pass filter. Active low-pass filter. So this was analysis, or not analysis quite, but explanation of the frequency domain. Right? When we change the frequencies, we can use the circuit as a filter. If you analyze the same circuit in the time domain, it works as an integrator. Capacitor current I is C dV over dt. Capacitor voltage V is integral of the current IC. VC is, excuse me, 1 over C integral of the current. So when you take the output V out and you analyze the circuit in the time domain, V out will turn out to be an integral of V in. So the circuit, the same circuit performs mathematically as an integrator. If you apply sine waveform to this, you'd obtain a cosine. Applying a cosine, you get sine. If you apply a square waveform as the input, you obtain a triangular waveform at the output. So it works as a integrator. Okay. All right, questions? So this is where I stopped for the previous class or the previous section. So this is where we'll stop for this class too. Look up the homework. I can't remember the due date. Sometime this week on it's tomorrow, so I'll extend that. I'll look at the problems, and if we haven't covered enough of the material, then I'll push it back by 1 or 2 days. So, but do get started on the homework. Based on the material that we have covered, there should be plenty of questions you can answer. Okay, and then if you have any questions, reach out to me. Let me know. All right, we'll stop right here, and I'll bid you a good day and see you on Friday.